Righty, hello year 12. So we are moving on to topics. Today we are looking at momentum. We are only going to have one video on this because we're a bit behind on schedule and you should have already covered all of this last year. Alright, so as I'm sure you are well aware of what momentum actually is, which is a property of moving objects and is defined by the product of the mass and the velocity of an object. Okay, we're also going to look at kinetic energy, Newton's second law of motion, and how to derive the formula for momentum. Right? So, the formula for momentum is given by a P, which has always annoyed me, but that's alright. P, and it is a vector quantity, so it has an arrow on the top. Therefore, it has direction and magnitude. Right? So, this is your formula. You've all seen this before. This is your friend. Alright, now, P is momentum, M is mass, and the V is velocity. The velocity. Yes, okay. Units for momentum is kilograms per meters per second to the -1. Mass, as always, is kilos, and velocity is meters per second to the -1. Once again, like this, no new information. All this stuff should be familiar to you. Okay, ready. So there are some examples here. We'll go through one. So if you have a truck at a mass of 4 times 10 to the power of 4 kilos, it's traveling at 25 meters per second. What's the momentum? Momentum is equal to mass times speed. Our momentum is unknown. Our mass is 4 times 10 to the power of 4. And your speed, your velocity is 25 meters per second. 25 meters per second, -1. So we have written out our formula, what we're looking for, and the values that we do have. Plug the whole thing into the equation. So P equals 4 times 10 to the 4. Put that in brackets on your calculator. It also helps if you write it with brackets, so that way when you go to punch it into the calculator, you immediately put the brackets in anyway. 25. Let me write that out. Weight in brackets because this belongs to that. And then the speed, which equates to 1 times 10 to the 6 kilograms meters per second -1. Okay? That. Once again, make sure you write your units. Okay? Do not forget to write your units. If you remember nothing else from physics, at least that you remember, write your units. Okay? Right. We also look at kinetic energy here. So again, kinetic energy shouldn't be new information to you. We have a formula for it. So capital E for energy, lowercase k, the subscript k for kinetic energy, so you know what energy you're dealing with. Formula is 1/2 mv squared, which is a lot like the acceleration formula. Looks very similar. Alright. So E, K, M, V. You all know what these stand for. That is my kinetic energy. Okay. And the symbol. So the symbol for energy is joules. That is the units that it uses. Mass is M. Velocity is V. That does not change. Okay. So formula for kinetic energy. Energy, capital, lowercase, little subscript k down here. Kinetic energy is equal to 1/2 times mass times velocity squared. I can't tell if this is backwards to me or to you. Anyway, so kinetic energy, EK is kinetic energy, given in joules, and you have mass, given in M, the unit, and velocity is V. That does not change. So if we want to solve a kinetic energy question, say for example, we have an elephant that has a mass of 3 times 10 to the 3 kilos and travels at 5 meters per second. What is its kinetic energy? So our EK is unknown. Our mass is 3 times, well, 3 times 10 to the 3. And our speed is 5 meters per second. We plug all of that into our equation. So it looks like this. The bottom one there looks like this. And then you stick that into a calculator and you should get, oh, I missed squared. Do not miss the squared. That should be squared of the top there. Don't forget that. That should equal to 3.75 times 10 to the 4 joules. Units. Do not forget them. Joules. Alright, next. Looking at deriving the formula. What is this? Mathematics. Okay, this is looking at momentum over a period of time. Okay, before we get to that, we are looking at how to derive that F equals delta P over delta T. Okay, so how to derive this formula? How do we get there? Let's go over it. So, your regular equation for force is F equals ma. Okay? You know that. Your formula for acceleration is A equals delta V over delta T. Okay? This is what we have. This one here is what we're trying to find. This is the obvious formula. Now we're going to substitute for our acceleration formula, which is this over here, into here. Okay? So we get F equals m outside of delta V over delta T. Right? Now, the m, the mass, goes to the top because if we were to write it over here, it'd be m over 1, as you would learn in maths. Okay? We have that. If we extrapolate that out, we have F equals m outside of V minus V naught, close the bracket, over change in T. And then, hello, what's this? This is the equation for momentum, because m times v is momentum. Hello there. So we can change that to F equals momentum, that's a P, minus initial momentum over the change in time. And what do you do when you have a final take the initial? You change it to a delta symbol. So then we have force equals change in momentum over change in time. Alright? That is how you derive the momentum, the force momentum formula. There's steps there. That's it. It sounds a lot scarier than what it actually is. But these are all formulas you have seen before. You got this. You can do it. Okay? So when if you ever get an exam question that's like derive Newton's second law of motion, this is what it wants. Okay? That whole entire process. Okay. So, next, looking at change in momentum. So, as all coordinate systems, left is negative, right is positive when you're moving in directions. That doesn't change. Alright, so we have the question. So before that, change in momentum on object is either speeding up or slowing down, similar to acceleration, or it changes direction. When solving problems involving the motion of an object in one dimension, change in momentum is equal to the final momentum subtracting the initial momentum. Coordinate system is used when initial and final momentum have opposing directions. I said that way too quickly, but it is on page 54 of your textbooks. Okay? So, looking at the example, we have a 160-gram bowl moves to the left of a page at 1.5 meters per second when it collides with the table and moves to the right of the page with no change in speed. Okay? So, let's go. First of all, we are looking for the change in momentum is unknown to us. But we can figure that out. So, momentum, change in momentum is equal to mass times speed minus mass times final speed. Sorry. Let me just show you. So, momentum is equal to mass times final speed minus mass times initial speed. Okay? So, we know that the bowl was 160 grams. 160 grams, which is equal to 0.16 kg. And we know that the initial speed and the final speed is 1.5 meters per second. Is the initial speed. And now, because the ball is moving to the left, the initial speed is negative. The ball is moving to the right, it'd be positive. So remember, when you're working in coordinate systems, if something is moving to the left, it is negative. If the object is moving to the right, it is positive. Okay. Right. So, before we move on, we have our values, mass, converting from grams to kilos, and then we have our initial speed and our final speeds there. Righty. So, we then plug that into our equation. So change in momentum is 0.16 times by 1.5, close the bracket, take 0.16 times negative 1.5, close the bracket. That gives us, if you plug the whole thing into your calculator, you end up with 0.48 kilograms meters per second negative 1. Now it is a positive number, so therefore that momentum is traveling to the right. Okay, make sure you write which direction your thing is traveling in. Right, which way it goes. Remember, magnitude and direction. Think of Despicable Me. Okay, magnitude and direction. Right, next, so calculate the average force exerted by the table on the ball in the collision which lasts 1.2 meters. Meters? It's meant to be milliseconds. It's milliseconds, which is really weird because it's also ms. Anyway, back to this. So, we have our force is equivalent to our change in momentum over our change in time. Remember, we derived the force formula earlier. Okay, change in momentum over change in time. So, our momentum is 0.48 positive because it's going to the right. And our time is milliseconds, which is 1.2 milliseconds, which is equal to 1.2 times 10 to the negative 3 seconds. You know how to convert between milli and regular and centi and all that. You know how to convert between all the prefixes. That's what they are. Okay, so we plug that into our equation. So we get F equals 0.48 divided by 1.2 times 10 to the negative 3 equates to 400 newtons to the right. Once again, positive newtons. Positive force moving to the right because we're in a coordinate system. We have this looking thing. Force, that's our formula. Our values, plugging our values into our formula, getting the answer, and direction. Right the direction. Alright, next. Calculate the acceleration of the ball due to the collision. Going back to when we derived the formula. So we have F equals ma is our usual formula. We rearrange it now to A equals F over M. Okay, so we know our force. Force is 400 newtons. We know our mass. Okay, they did 160 times 10 to the negative 3. They just done 1.6. Sorry, 0.16. It doesn't matter. Anyway, so we have our force, we have our mass. We plug it into our equation, 400 divided by 0.16, which equates to 2,500 meters per second. Negative 2 because it's an acceleration, and it is positive, therefore it is moving to the right. Okay, okay. Last part of it. We're finding the acceleration, A equals F over M. Force, 400 newtons. Mass, 160 times 10 to the negative 3. You can just write 0.16. It's a lot easier. Then you do force divided by mass. You get that? And don't forget to write the direction in which it is going. Alrighty. This is the same for pretty much all momentum questions. Except for vectors. Because yes, you can have momentum vectors because, once again, vector quantity, direction, and magnitude. Alright, and for that, you use vector subtraction and addition. Once again, should learn in maths. Okay, so looking at example 1.27, you have basketball playing with the ground at a speed and an angle 45 degrees to the horizon. Determine the change of momentum if the basketball rebounds with no change in speed. We are also assuming no change in angle either. Okay, alright, vector subtraction. What? I know what this equation is. I don't remember what the name of this thing is. There's a name for this formula. I don't know what it is. Pythagoras. That's what it is. V squared equals V squared plus P squared. Oh. Yes, so we're using Pythagoras to solve this. So right, I'm sure you guys all know how to do Pythagoras. I don't need to walk you through this example. I'm still gonna walk you through it anyway. So with our information that we have the mass 0.625 grams. We have the speed. Okay, so we sub those in for momentum instead. Now, don't forget, because this is rebounding, they're going to have a positive and then a negative momentum. Hold the phone, never mind, it's Pythagoras, we're not looking at that. Alright. This. Okay, so with the vector diagram, do not forget that if you are subtracting, it's you have an angle like this and the opposite angle this way. You move the opposite angle to the other side of the positive angle, and then you draw the subtraction line that connects the two together. Which, let's actually draw that so it makes sense. Yeah, 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 yeah. Negative P naught. Change in P. Okay, so the whole thing. Using Pythagoras to figure out what the change of momentum is. That's this long line here. Yes. So we have with vector, this is our initial vector. Then we have our opposite vector, which we're drawing on a bouncing ball. It'd be bang, bang. We move it from down here to up here to get a nice triangle because we're doing a subtraction. Then we work it out and you got it. That's it. Right. Got all the questions on momentum. Almost. Okay. So, next, Newton's third law of motion, which I really hope you're all familiar with, or else you're going to have a rough time, which is, for every action, there is an equal and opposite reaction. When applied to forces, it means if you're moving something one way, there is an equal and opposite force moving in the other way. So, if I move this water bottle that way, across, there is another force hitting it away. So, and my pushing force needs to be bigger than the preventative force to stop it from moving. Of course, I'm continuously pushing it, so, you know, it's a bit easier. But if I was just to push it once, it stops, right? Because you just like see the lid sliding closer to you. If I push it too hard, it falls over. Alright, so the mathematical formula for that, well, not the mathematical, the formula that we use for Newton's third law is F equals F1 is equal to negative F2. Every action, there's an equal and opposite reaction. For every force, there is an opposite force that is equal to it in the opposite direction because it's negative and the positive. So, there is a diagram on page 60 that describes this. You have two balls, you hit them together, and then they're going to, the moment of impact, you have one that's a positive force, one that's a negative force. They are equal in size, and then they rebound when they hit each other. Okay? Alright, conservation of momentum is the name of this formula. So, if we were to derive that, it would be F1 is equal to negative F2. Okay? Write the F out. So instead of writing in force, you swap it out for the momentum formula, the force momentum formula, which is equal to change in momentum divided by change in time is equal to change in momentum 2 divided by change in time. The times cancel out because they are the same value, so you can cancel them out, which equals the change in momentum is equal to the change in the negative change in momentum. Okay, and then you bring the negative over to the positive, and that should always equal to 0. Okay, so look at this. Force 1 equals negative force 2. Change in momentum 1 over time is equal to negative change in momentum 2 over time. These two cancel out. So we rewrite them as change in momentum is equal to negative change in momentum. We bring this to the other side. When you add the two different momentums together, you should always get 0. Okay? The net force of two equal forces hitting each other is 0. Moment of collision, force is 0. Alright, when you have a system, so 3 or more things hitting each other, it gets a bit more convoluted. So you end up with something that looks like the change in momentum total is equal to each change of momentum added together. Okay. So the equation looks something like this. All of these together. That's a T. So change in momentum total is equal to change in momentum 1 plus change in momentum 2 plus change in momentum 3. Add these three together, get the total change in momentum. Alright, and when it comes to forces, it's a little messy drawing the force diagrams because you have to have your 3 objects, number them, make sure you number things. Alright. So you have force 1 acting on force 3 acting on force 2 on 3, 2 on 1, and 1 on 2. And then you have the forces acting outside because they hit and they rebound. Alright, which would be your force external. Okay, so F, E on 1, F, E on 3, F, E on 2, F, 3 on 2, F, 2 on 3, F1 on 3, F3 on 1, F2 on 1, F1 on 2. Okay? Got a lovely slightly incommensurate diagram. So we have 1, 2, 3. On the outside of the mole, we have our external force, which is being pushed away. On the inside, so this is force 1 acting on object 2. This line here is force 2 acting on object 1. This line is force 3 acting on object 1. This one is force 1 acting on object 3. Force 2 acting on object 3. And force 3 acting on object 2. A little bit confusing? You got this though. There is a much neater picture on page 61. Suggest you look at them. Okay, ready. And then it's just a bunch of questions and examples. Okay, which we will skip over. Alright, and what is this? Yeah, still on. Okay, so next we have multi-image representations. Okay, so multi-image representation is a diagram showing the motion of one or more objects in a series of images and is used to determine whether momentum is conserved in a collision or an explosion. Alright, so you draw vectors throughout the entire thing, and I really don't like doing these. That's okay, they are very helpful. They're just a pain in the butt because I'm not great at drawing, so that's why I don't like doing these. Alright, so multi-image diagram shows a collision between two particles A and B. The mass of particle A is equal to the mass of particle B. This is an example, by the way, example 1.35. Alright, in this example, vectors are drawn between the centers of an equal number of images as particles have equal mass. Momentum is conserved in this example as the total momentum vectors have the same length and direction. That's another thing, when you are doing these things, take an ruler in with you to the exam so you can check to see if these are equal length. Because if it doesn't tell you, you can assume it or not assume it. So take a ruler, make sure they're equal lengths. You can claim that as evidence, I guess. Alright. So, I'm not going to draw this, I'm just going to show you. We have our... That's worse. That's definitely worse. Okay, but we have our diagram. Yeah. Down the bottom, they've drawn in the vectors. So these are the objects that are moving, one here and one here. They have drawn vector diagrams at the start and at the end of each pathway. Okay? And upon measuring and mathing, they have realized that the start vectors, that these vectors are the same. Okay? So the momentum before the collision, they've drawn a vector diagram for it, and the momentum after the collision, they've also drawn a diagram for it. Alright, you can do the same thing if you have multiple points of impact. So you can also do the same if you have 3 things hitting or 4 things hitting each other and whatnot. You do the same thing. Have the diagram drawn out, draw your vectors through, assume that the vectors form a closed triangle. If your vector diagram forms a closed triangle, it means the momentum is conserved. Doesn't matter how many things you have, closed triangle, conserved momentum. Right. Questions? Ready. Next. Conservation of momentum can also be used to explain propulsion of spacecraft, ion thrusters, and solar sails. I love solar sails, that's so cool. Alright. So, this is a whole bunch of information explaining how these things work. I'm not going to read it to you, but page 78 and 79, all the information that you need that explains how solar sails and space shuttles and ion thrusters work. Yes, you do know how to. You do know how. You do need to know how those things work. Because when it comes to exam time, you will get an information. You will get there's usually a question about how does this work, or like in 2010, someone launched this blah 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 thing using a solar sail or ion thrusters or some sort of jet propulsion. How does it work? And then you have to go through and explain how it works. Alright, that is it for momentum. So, suggest you fill in and go and do all the questions in your book. I'm not going to go through and tell you the pages, you can do that, but the chapter for momentum that we've just covered goes from... That's not it. From page 52 to page 81. So any questions, pages that are between page 52 and 81, go for it. Alright, that's all. Goodbye.